Hello students, this PPT is regarding decoding of BCH code. This is the preamble slide. To decode the BCH code, you will require to refer the table of primitive elements which we generated in BCH encoding. So if I am referring to GF16 field, I want you to refer the slide where we have calculated the elements 0, 1 up to alpha raised to 14. Because in the substitution of syndromes and all other calculations which are essential for BCH decoding, you continuously need to refer the table where we have generated all the 16 elements of GF16 field. If I am talking about GF8, then you need to refer the respective table. But in this particular PPT, I am going to demonstrate the BCH decoding of GF16 field. So this is the preamble slide. The actual problem will start from slide number 3. On slide number 2, the table is again given for your reference. So you please refer the table on slide number 2 when you actually solve the numerical. So it's BCH decoding procedure. We are assuming that our BCH code has error correcting ability of 2 bits, so TC is equal to 2. So the corresponding generator polynomial is x raised to 8 plus x raised to 7 plus x raised to 6 plus x raised to 4 plus 1. How we got this generator polynomial? This was completely explained in the previous PPT of BCH encoding. So please refer the PPT for this GX. So now we got message as 0010011. We have assumed that it's any arbitrary 7-bit message. Right? So mx is equal to x raised to 4 plus x plus 1. Why we have a 7-bit message? Because my generator polynomial has degree of 8 and n is equal to 15. We are referring to GF16 BCH code. So my message will have length equal to 7. Again, this was completely explained in BCH encoding. So you can again refer that particular PPT. So my Cx is mx into gx. We are assuming it's a non-systematic cyclic code. So mx into gx, my mx is x raised to 4 plus x plus 1 into gx is my corresponding code word polynomial. So the code word polynomial is given in the slide: x raised to 12 plus x raised to 11 plus x raised to 10 plus x raised to 9 plus x raised to 8 plus x raised to 6 plus x raised to 5 plus x plus 1. When you convert it into binary coefficients, it will be 1 1 1 1 1 0 1 1 0 0 0 1 1. So total 13 bits. And let the received code word is 1110 1011 01011. Right? So see the convention, the received code word, the last bit, the LSB is called bit 0, the next bit is bit 1, bit 2 and so on. So the last bit or MSB in this case is bit number 12. So bit number 3 and bit number 9 are in errors. So right now we know this, but assume that you are a receiver. So you received the code word which is having error at 2 different locations. So as a receiver, you don't know which 2 bits are in error and you need to detect them and correct them. So as a step 1, you construct the received code polynomial. You have received the code word, so convert it into polynomial. So R of x is the received code word polynomial, which in this case is x raised to 12 plus x raised to 11 plus x raised to 10 so on up to x plus 1. Now we need to calculate 2 TC of syndrome. Again, what is TC? Error correcting ability. So as TC is 2, 2 times TC is 4. So we need to calculate 4 syndromes to calculate the error. Okay, so the first syndrome is, how do you get the first syndrome? Put x is equal to alpha in the received polynomial. So R of x will be replaced by R of alpha, which will be alpha raised to 12 plus alpha raised to 11 plus alpha raised to 10 plus alpha raised to 8 plus alpha raised to 6 plus alpha raised to 5 plus alpha cube plus alpha plus 1. And now for alpha 12, alpha 11, alpha 10, you refer the table of primitive elements, and alpha raised to 12 is alpha cube plus alpha square plus alpha plus 1, alpha 11 is alpha cube plus alpha square plus alpha. These values we got from the table of primitive elements. So the first syndrome which we get from this after cancellation, S1 is equal to alpha. Now we calculate second syndrome. So in that case, you need to replace x by alpha square. So when I replace x by alpha square, we got r of alpha square as alpha raised to 24 plus alpha 22 plus alpha 20, alpha 16 and so on. Now alpha raised to 24 is alpha 9, because again if you refer the table of primitive elements, alpha 15 is 1. So alpha 24 will be alpha 15 into alpha raised to 9. So which is alpha raised to 9. Similarly, alpha 22 will be alpha raised to 7, alpha 20 will be alpha raised to 5, alpha 16 will be alpha, and so on. So again, when I write the values of alpha raised to 9, alpha raised to 7, alpha raised to 12 from the table, we get the second syndrome. We indicate the second syndrome as S2, and we got the second syndrome as alpha square. Now for third syndrome, we put x is equal to alpha cube. So r of alpha cube will be alpha 36 plus alpha 33 up to alpha cube plus 1. Now again alpha 36 will be alpha 30 into alpha raised to 6. As alpha 15 is 1, alpha 30 will be again 1. So alpha 36 is alpha raised to 6. Alpha raised to 33 is alpha cube. So you calculate all these values, and the third syndrome which we get from these calculations is alpha raised to 8. For the last and fourth syndrome, we put x is equal to alpha raised to 4. So r of alpha raised to 4 will be alpha raised to 4 after simplifying, following the similar steps of simplification. Now step number 2 is the step of matrix multiplication. Now we got 4 syndromes. Now this step is very important. You should remember this matrix of multiplication. So if you refer the first matrix, it is S1, S2, S3 up to SP is the first row. Second row is S2, S3, S4 up to SP plus 1. And the last row is SP, SP plus 1 up to S of 2P minus 1. So this matrix is matrix of syndromes. The rightmost matrix, the matrix on the right hand side is SP plus 1, SP plus 2 up to S of 2P. So it is also matrix of syndromes. And in between you have matrix of lambdas, lambda P minus 1 up to lambda 1. So P in this case is error correcting ability. So we will have S1, S2 up to S2, right? Because P is error correcting ability of this. So lambda will be roots of the equation, which we will see in the next slide. Okay, so as we discussed, P is number of errors. In our case, P is 2. So 2P minus 1 will be 3 and 2P is equal to 4. So if you refer the matrix, it will be S1, S2, S2, S3 into lambda 2, lambda 1 is equal to S3 and S4. See again, if you refer the previous slide, it is S1, S2 up to S of P as the first row. As P is 2, the first row is S1, S2, and the last row is SP up to S 2P minus 1. So the last row will be S2 and S3, and then you have lambda P up to lambda 1, but P is 2, so it will have lambda 2 and lambda 1, and the third matrix is S3 and S4. So now our aim is to solve for lambda 2 and lambda 1, because lambda 2 and lambda 1 are later on used to calculate the error locations. So if we put the values, S1 is alpha, S2 is alpha square, then again S2 which is alpha square, and S3 is alpha raised to 8, then lambda 2, lambda 1, and then we have S3, S4, that is alpha raised to 8 and alpha raised to 4. So now we want lambda 2 and lambda 1. I am calling this left hand side matrix as M. So lambda 2 and lambda 1 will be M inverse into right hand side matrix. So it will be M inverse into alpha raised to 8 and alpha raised to 4. Now you already know how to calculate matrix inverse. So it is adjoint of M upon determinant of M. So if you calculate this adjoint of M, it will be alpha raised to 8, alpha square, alpha, and determinant of M will be cross multiplying alpha into alpha raised to 8, which is alpha raised to 9, and alpha square into alpha square, so alpha raised to 4. So if you put the values of alpha raised to 9 and alpha raised to 4 from the table of primitive elements, you get alpha raised to 14. So you have adjoint of M, which is numerator, upon the determinant of M, which is alpha raised to 14. In this case, we are calculating inverse of the matrix. This has a great significance. If inverse of the matrix doesn't exist, that means the determinant is a zero element. So if it is a singular matrix, what is meaning of that? So right now we are constructing the matrix assuming there are two errors. If this matrix is a singular matrix, that means if the determinant of this matrix is 0, that clearly indicates the inverse doesn't exist, and the meaning of that is the received code word has less than 2 errors, right? Suppose you assume that there are 3 errors, so you will have 3 by 3 matrix. Right now there are 2 errors, so you have 2 by 2 matrix. If you have 4 errors, then you will have 4 by 4 matrix. So let us assume that there are 3 errors hypothetically, so you will have a 3 by 3 matrix. And if the inverse of the matrix doesn't exist, then that clearly indicates there are less than 3 errors. Then we have to construct 2 by 2 matrix and again see if its inverse is existing. If the inverse exists, then there are 2 errors. If that inverse is not existing, then that clearly indicates there are less than 2 errors, right? So continuing our example, you got M inverse is alpha raised to 8, alpha square and alpha upon alpha raised to 14. Now 1 upon alpha raised to 14 is alpha. How? Because 1 is alpha raised to 15. So effectively it is alpha raised to 15 upon alpha raised to 14, which is alpha. So you are dividing the numerator matrix by alpha raised to 14 is equivalent to multiplying that matrix by alpha. And if you do that, then M inverse is alpha raised to 9, alpha cube and alpha square. Yes, so what is lambda 2 and lambda 1? M inverse into the right hand side matrix, which we have already seen on the previous slide. So lambda 2 and lambda 1 will be alpha raised to 17 plus alpha raised to 7, which is lambda 2, and lambda 1 is alpha raised to 11 plus alpha raised to 6. So we get lambda 2 and lambda 1 as alpha raised to 12 and alpha. Now the last step is form the polynomial of lambda. Now you got two values of lambda. So your polynomial is lambda 2 x raised to 2, that is lambda 2 x square plus lambda 1 x plus 1. That 1 is always implied. Suppose you have 3 values, lambda 3, lambda 2 and lambda 1. Then your polynomial will be lambda 3 x cube plus lambda 2 x square plus lambda 1 x plus 1. So again you see the 1 is implied here, right? So there are 2 values, so our polynomial is lambda 2 x square plus lambda 1 x plus 1. So if you put the values, it will be alpha raised to 12 x square plus alpha x plus 1. Now we need to find out roots of this polynomial. The highest degree of x is 2, so second degree equation. So you will have 2 roots of this particular equation. Okay, so the last point, very critical point. You want 2 roots such that their multiplication is the coefficient of x square, which is alpha raised to 12, and their addition is coefficient of x, which is alpha. So what are the possibilities here? Let's consider the multiplication. So multiplication should give you alpha raised to 12. So my combinations are alpha and alpha 11, alpha square and alpha 10, alpha cube alpha 9, alpha 4 alpha 8, alpha 5 and alpha 7, and alpha 6 and alpha 6. So if you see all the combinations, we got the third combination, which is alpha cube and alpha 9. If you add them, the answer is alpha. So the 2 conditions are satisfied here. The multiplication of alpha 3 and alpha raised to 9 is alpha raised to 12, and addition of alpha cube and alpha raised to 9 is alpha. So the required roots are alpha cube and alpha raised to 9. These roots actually indicate the bit number which are in error. So if you refer the code word, our error locations are 3rd bit and 9th bit. So again I am giving you the received code word. The received code word was 1110, 1011, 0110 and again 11. And we saw bit number 3 was in error and bit number 9 was in error. I have also given you the actual code word, which was the last code word, right? So these 2 bits were in error. So now alpha cube and alpha 9, they indicate the bit number 3 and bit number 9, they are in error. And as these are the binary codes, you just have to invert the bits. So wherever you have 1, if that is in error, you make it 0, and wherever you have 0, you make it 1. So this is how you decode the BCH received code. This is very important. Just go through the slide once again, try to solve this numerical on your own, and we will have further slides, few presentations that I will be uploading very shortly.